There will be no audio for the first 5 minutes of this class. What's that? It was? That's interesting because it wasn't on. Anyway. Okay, so now I'm talking. And so the first like kabuki theater or something. So what do I need to do to swap in a page? Yeah.
Want the page to swap out?
Yeah, I better find some memory, right? So I have to stop the instruction. We just talked about that. That generates an exception. I need to allocate a page in memory. What might I need to do here in order to find a page? Swap out, right? If memory is completely full, I might actually need to swap a page out, right? So this can get messy. What else? What's the sort of obvious thing I need to do? Yeah. Yeah, copy, well, I gotta locate the page, right? So I need to find the contents, copy them in, right? Okay, now this last two little things I need to do before I can restart the instruction. Doug, what's one of them?
Update the page table entry so that you know that's in memory.
Right, so I want to update the page table entry because the page is moved. The page is now in memory. And then in order to allow the process to use the memory, what do I need to do? Yeah? Update the TLB. And then I can restart the instruction. Right, so this is, any questions about this? You guys, will, this is kind of, I think it's the first year where there's been like any real unintended synchronization between lecture and the assignments, right? So you guys just saw these instructions. This is more or less a vague description of what you guys will need to implement for assignment 3. All right. We talked about two different types of faults, and this was related to software and hardware managed TLBs. A TLB fault occurs when a page is not in the TLB but in memory, and a page fault occurs when the virtual page is neither not in memory or doesn't exist yet because it hasn't been initialized, right? All right, we don't need to go through this again. Yeah, we did on-demand paging. Yep. Okay. Any questions about swapping, on-demand paging, hardware TLBs? Yeah, Adam.
Even though it would technically be thrashing, is it possible for a system to run only on hard disk?
Wow.
I think I've seen it.
Is that a system that you built?
No, like wasn't that a really old computer, and you had about 2 gigs of like visible swap space at the top of the C drive for some reason on a Windows XP.
Huh.
It was weird.
Oh wait, sorry. Do you mean is it possible for the system to run out of swap space?
Run only on the swap space. Well, I don't think it would swap space that
I don't think so, because you need at least a page of memory, right? Because otherwise you just can't use load and store period, right? Because remember, if you had well, I don't know. I don't want to box myself in here. A page might not be enough, right? And in fact, I think actually if you only have, I think this was an exam question once, if you only have a page of memory, this might be in the assignment 3 code reading questions. If you only have a page of memory, it's possible that you can, that system can get into loops trying to handle page faults, right? Yeah, that is in the questions, right? So I have 1 page of memory. The process faults on it. In the process of handling the fault, I need to fault in the code to run it into memory, so that faults that page out, right? So you can see that I don't have enough pages to make any forward progress. So I guess if I can't do it with 1, I probably can't do it with 0, right? It's a good, interesting question. Good question. Any other questions about? Yeah.
Suppose I have a process with multiple threads and there are multiple cores.
Uh-huh.
So suppose one thread, the page fault occurs for one thread and the kernel is doing whatever swapping and stuff like that. And during that time, another thread runs on another core, and it also creates a page fault. So how does the kernel handle that?
Okay, it's a good question. So let's say I have a multi-threaded process. This could actually occur on the same core too, right? A multi-threaded process. One thread A faults on an address in their shared address space. The kernel starts faulting that page in from disk. What happens to thread A while that process is going on? Has to go to sleep somewhere, right? We're talking about I/O. It's going to take a while. It's not going to sit there busy waiting, right? I'm going to put it to sleep on some sort of wait queue. I'm going to let other things happen. The other thing that I let happen might be running another thread from that same process. So now thread B starts to run. It's running along happily until it faults on the very same address. So what needs to happen to thread B? It's a good question. I mean, if thread A hadn't come along, what would thread B do? Swap in the page, right? It would initiate a swap in of the page. So instead of it, because thread A has already done that, right? So that page is on its way in from disk. What should thread B do? Until when? Until the page makes its way in from disk, right? So, and this is actually a case where you guys will have to handle for assignment 3. Right? You will have cases where there are pages in memory that are what are called busy, right? Or that's one way of thinking about it. That page is in a weird state, right? The kernel may have already allocated the memory for the page, but that memory hasn't actually had the contents loaded in properly. So essentially, the second thread needs to just sleep until that I/O completes. And you need a mechanism for figuring out when to wake that thread up properly. Does that make sense? That would be the same thing on multiple cores.
Yeah, one more question. Is the kernel multi-threaded to handle multiple threads?
Yeah. Yeah.
It has to do the same operations on different cores, right? So the kernel has to do the same operations for every TLB.
Right. So the kernel has to manage per core TLBs, right? So essentially, what would happen at the end on your multi-core example would be that there would be a mapping for that virtual to physical translation for each thread on both cores. So core A, where thread A was running, would have a mapping from the virtual to physical page, and so would core B, right? Now, what does that mean if I want to later evict that page? Let's say later, I've run out of memory and I need to choose a page to swap out, and I'm stuck choosing a page that's not only in one TLB, it's in 2 TLBs. So what has to happen at that point? Remember, the first step in swapping out a page was removing the translation from the TLB. So how do I generalize this to multi-core systems? Yeah. Yeah, so I actually have to get the entry out of every TLB on the system. And it turns out that this gets a little more complex because cores typically don't have direct access to the TLBs on other processors. So actually what I need to do is I need to send the other processor a message of sorts and get it to remove that entry from its TLB. Right? You guys actually, I think there's a variant of this that's implemented on your OS 161 system. So I need to have some mechanism to allow one core to signal another core and say, by the way, there's this problematic entry in your TLB that we need to get rid of. Does that make sense? Cool. All right, so today, let's get through all this crap. All right, so today is entirely concerned with that one pesky step when I swapped a page in, or essentially the process of swapping in, or just allocating new memory. Right? When I run out of memory at some point, I'm going to have to make this decision, which is what page should I evict? And this might happen when I'm swapping in a page that's been faulted on by another process. That's not an ideal time to do this because it makes that page fault even slower. So a lot of systems will try to make sure that there's a small amount of memory that's always available on the system so that if I suddenly get a bunch of page faults, I have some memory to load them into without having to immediately throw stuff out. But it means that as time goes by, I need to trim pages from memory, and I still have this problem, right? And the problem is quite simple. It's which page should I move to disk, right? So this is one way of thinking about this is a cost-benefit calculation. What is the cost to evicting a page? What is that measured in? What's the cost that's actually borne by the operating system in order to evict a page from memory? Yeah. Okay, time. Yeah, that's true, but the time for what? Yeah, it's the cost of actually doing the time and the disk bandwidth to some degree, right? This I/O is going to compete with other operations that the disk is doing. We'll talk more about disks on Wednesday. But it's also the time, right? While I'm doing this, that page is busy and certain other things can't happen, right? Essentially, also, I don't really have a good way to have access to the page contents while the page is being swapped to disk, right? And the best way to think about this is that when I swap a page out, it's probably also coming back in at some point. And so I really need to consider the cost as being both the I/O to get the page to disk and the I/O to get it back, right? What's the benefit? This sounds terrible. Why do this at all? Yeah, Kevin. Yeah, the benefit is that I get 4K of memory, right? 4K of free, clean, clear title memory that is now unused, right? So there's 4K more memory on the system. The cost is that I've had to do some I/O, right? And there are these tricks that I can use to minimize the cost. I do batch these operations and try to optimize I/O to the swap file and stuff like that. But today we're going to mainly talk about ways to maximize the benefit, right? So, sometimes when people talk about the performance of these algorithms, they talk about minimizing the page fault rate, right? So the number of pages I have to bring in from disk, right? So one way of thinking about this is if I choose the wrong page to throw out, then that page is going to come right back in fairly quickly. And so if I have a bad page replacement algorithm, it's actually going to generate a lot of page faults. A good page replacement algorithm is going to generate fewer page faults for the same workload. Okay. All right. So when things get really bad, and many of you, I don't know, maybe thrashing isn't as obvious on sort of flash-based systems, but those of you who are old enough to have used a system that had a real disk in it that spun around in circles probably have experienced this sort of, how many people have ever had a system that they knew was thrashing, right? How do you tell? What's that? Yeah, you actually can tell from the sound, right? You hear the disk like, got this very characteristic sound to it. But what else? What else can you tell? How else can you tell?
Everything else gets really, really slow.
Yeah, nothing else works, right? The system is like not making any forward progress. And so in certain cases, and this isn't always the function of bad page replacement algorithms, you may just have asked the machine to do more than it's really supposed to be able to do, right? But at some point, when the overhead of trying to use more memory than the system is really supposed to have, and all of the I/O that goes on to move pages to disk starts to overwhelm the performance of the system, you have this sort of colloquial condition that we call thrashing, right? Thrashing is one of those things that may be difficult to define in some rigorous way, but is very easy to detect, right? At least very easy for a user. Okay, so when we talk about maxing the benefit of these 4K of memory, how do we do that? I mean, it's 4K, right? So what? It doesn't seem like there's really a knob here to turn, right? What do I want to optimize about this 4K in order to maximize the benefit from doing the I/O to move the page back and forth to disk? Adam.
Maybe if a process exits, we can get rid of pages that were only used by that process.
Okay, so in process exit, I can certainly evict their memory, right? That's not really swapping, right? That's just deleting those pages, destroying those pages. But again, I've got 4K. I've cleared up 4K of memory by performing this swap out operation. How do I make that 4K of memory as valuable as I can? Yeah?
Put something you use the most.
What's that?
Place something in it which you use the most.
I'm not even talking about what to put in it yet. I'm talking about what to put out. Yeah? Oh, you guys are describing an algorithm to me. And some of these algorithms might work OK. But I'm saying, how do I maximize the benefit of this particular slice of memory? So, yeah, you guys are getting ahead of yourselves. This is an interview question. How do I maximize the benefit? It's just 4K of RAM. Who cares? I want 4K for the longest period of time, right? I've just created 4K, okay? At some point, that page that I just threw out is going to come back and want its 4K back, right? It is. It's going to be like, hey, I want my memory back. You'd be like, okay. I mean, and it has every right to do that, right? And when it does that, you're going to have to say okay, because it's the application anyway. It was a bad analogy. The page doesn't really do that, but I want to find the page. So it's 4K, right? But it's 4K for how long? Who knows? It could be a long time. If I choose a good page, if I choose a bad page, how long could it be? We already talked about this a little bit before. If I choose the worst possible page, how long will it spend on disk? 0, right? By the time it gets to disk, it's already being swapped back in, right? Because remember, it takes a while to get to disk. So as the page is on its way out to disk, then the application comes and it's like, I want that page. And you're like, uh-oh. I need to wait for it to get to disk, bring it back in, or stop. A lot of times you can't stop the I/O. It gets terrible, right? You guys will have to deal with this with assignment 3. This will happen, right? And you're like, oh man, I wish I had a better algorithm. Okay, so what's the best, the absolute best page to pick? We talked about this a little bit on Friday, right? Yeah. That's right. There are pages like this. If I can find a page that the application has totally forgotten about, that will never be used again, right? Then that page is a great candidate for moving to disk, right? Because this page is the only page that will not come and want its 4K back, right? Because the application may not ever see it again. What's I mean, this sounds like sort of like a fantasy, right? But what's an example of pages like this? Give me a couple of examples of pages that might fall into this magical category. Yeah.
Any kind of initialization instruction?
Yeah, that's a great point. Stuff that's run during initialization that never gets run again, right? Sort of set up code sequences. That's a very good one. Yeah. What else? Yeah, Kevin. Okay. That answer is half correct. But why is it only half correct? That's right. If I'm doing on-demand paging, hopefully those never came in the first place, right? But certainly like a rarely used code path, when you accidentally fat finger Word and you open up some weird dialog box that you've never seen before and you're just like, quit as fast as possible. Like that stuff might go back to disk and never be seen again, right? What else though? Heap pages, right? Sometimes allocators will go through heap. They're not always that good at reclaiming stuff. So there's pages that fall into that category. All right, so now let's go back to thinking about scheduling. So scheduling was the last time that we talked about this type of policy decision. So when we talked about scheduling algorithms, what sort of information or what category of information did we really want to know about threads? And or how do you apply this to this problem? What would we really like to know when we choose a page to evict? If I had my crystal ball, what would I ask it? Yeah. Yeah, when is the next time this page will be used, right? How long before this page will be used again? Now, okay, so I don't have, unfortunately, sadly, again, a crystal ball, but this is the sort of optimal page scheduler, right? The optimal page replacement algorithm picks the one that will remain on disk for the longest period of time. And it's easy to convince yourself that this is true because this maximizes the benefit of the swapping operation, right? The benefit is 4K times how long the page is out. I pick the page that's out the longest, I do the best, right? Unfortunately, again, no one has succeeded in implementing this scheduler, this page replacement algorithm. You're welcome to try, right? It'd be quite an achievement. So, what do? We're operating system designers. When we can't predict the future, we use the past to predict the future. That's right. And one more time, we use the past to predict the future. Right. So, essentially, the way we're going to do this is, as people suggested, we're going to look for pages that haven't been used recently, right? Unfortunately, that may not mean that they're never going to be used again, but this is the best we're going to be able to do. And whenever we're designing a page replacement algorithm, we have to do a couple things. We have to figure out what information do we want to keep track of? How is that information going to be collected? When do we have a chance to see some of these things, right? Because unlike scheduling actually, to some degree, the operating system had more visibility over. Because a lot of address translation is being done by hardware. And hardware is helping us to make this fast. We now have this sort of tension here, right? Because we want hardware to make this fast, but hardware making this fast sometimes interferes with our ability to collect statistics about what hardware is doing, right? And then finally, we need to store this information without creating a massive amount of overhead for the system, right? Remember, all the information we use to store anything about page access patterns competes for legitimate uses of memory for the available memory on the system, right? So if we double the amount of state we need, it's probably not a good algorithm, right? And again, so collecting statistics could be expensive. I have to do this every time. Let's say, you might say, you know, this would be, I have a great idea. Let's count the number of times a page is written to, right? Or a page is accessed. That sounds like a reasonable thing to do, right? I'll just say, OK, well, that page has been used a lot. It's been used millions of times in the last couple of seconds. And so that's an important page. Keeping track of that state and actually having to bump a counter every time the page gets accessed. Remember, we wanted that access to be fast, right? It's like one lookup in the TLB and boom, right onto the memory bus. Now you've got some additional circuitry that's going on. There's some sort of counter somewhere. Yeah, not necessarily a greatest idea, right? And the storing statistics, as I just said, so that competes with memory for other stuff, right? All right, so back to, you can draw more parallels with scheduling, right? What is the simplest possible page replacement algorithm? A good benchmark, yeah. Random, yeah, that's our good friend, right? Our good friend random. Just pick a page at random to evict. What's good about this?
Really simple.
Simple, and it's a great baseline for algorithms that try to do better, right? Like we said with scheduling, if you can't beat random, just don't get out of bed, right? Yeah, you got to beat random. Cons? It's probably too easy. We might be able to do a little bit better, but there's especially with page replacement, there's a fine line here, right? We don't want to do too much more than random, right? We want to do better, but not the cost of too much, right? So what's an algorithm that would use what's a simple page replacement algorithm that used the past to predict the future of a page? Yeah.
The least recently accessed page.
Yeah, so least recently used, okay? So the least recently used algorithm is not that complicated either. I'm going to pick the page to remove that has not been used for the longest period of time, right? To some degree, this is intuitive, right? I mean, maybe the process forgot about this page, right? This doesn't always work, but doesn't work that badly. What's nice about this? What's that? Someone is saying something that sounds like an answer, but I can't parse it. This might be as good as we can do, right? And this is like we said with scheduling, this is another one of those cases where you can come up with, you're probably thinking there right now, man, I could do better than that, Like, I'm going to use the machine learning algorithms that I'm learning about in my other classes to like solve this problem. And I mean, I actually have thought it would be fun to try some of that stuff, just to see, but I have a suspicion that things would not work out all that well, right? That the overhead that you're introducing is not necessarily going to be great. But there's some problems with implementing this, right? The first is, how do we tell how long it's actually been since the page was accessed, right? And the second is, how do we store how long it's been since the page was accessed? So how do we collect the statistics that we would need to actually run this algorithm? When does the operating system know for sure that a process has accessed a virtual page? When we load the entry into the TLB. After that, how much do I know about whether the page is accessed or not? Nothing. That might have been the last time that the page was used, or every instruction that happened after that loaded from memory might have all hit this same TLB entry. I really don't know, right? No, right? Yeah, I just said that. Wow. Sometimes it's like I wrote these slides. All right. So, and again, why wouldn't I record every page access? Yeah, this would probably be too slow. Maybe you could get hardware that does. I don't know. It's a good question. Maybe there was a memory manager at some point that actually did something like this. But in general, it's too slow, right? But now let's come to the other part of it, right? So let's pretend that maybe you can design me a new memory manager that, in parallel with translating every virtual memory access through the TLB, also bumps a counter on the TLB that is accessible to the operating system, right? My second problem is, where am I going to put that stuff? How much access time information can we store? First of all, where is this going to have to go? Yeah, it's going to be in the page table entry, right? And let's say I have let's say I want to store 32 bits of access time, right? I mean, that actually might not be that long, right? 2 to the 32 ticks. It really depends on how long your unit of time is, right? I mean, we're talking about processors that are running at gigahertz frequencies, right? Meaning that you have tiny, tiny, tiny little bits of time. But this would double the page table entry size, right? Remember, we did all this work to cram the page table entry down into 32 bits, or at least make it as small as possible, because I'm going to have a lot of them, right? So I don't want these to overwhelm memory. Now I've just doubled the page table entry size. All that work I did was kind of silly, right? If I get 8 bits, then I get 256 ticks, maybe that's enough, right? I think, how many bits do we have left when we finished before? It was like 6? Okay, so now I can do like 64. Yeah, that's not too bad. And then how do we, now here's the other question. How do you find the least recently used page? Okay, I've had a page fault. I'm looking for new memory. The process is stuck there waiting on me. And now what do I do? I need some sort of efficient data structure that actually has to hold every physical page on the system that is searched on every page eviction, right? I could probably find a way of making this not terribly bad, but it's still overhead on every page access, right? So instead of actually doing real sort of full strength LRU, a number of systems use a variant of LRU that's called the clock, that we always have to teach because it's a clock. Like, we get to have a clock. Anyway, I don't know. Maybe that excites me more than you, apparently. So, but clock is interesting. It's sort of it's a variant of LRU. It's not quite pure LRU, but it has LRU-like properties, and it's much more efficient to implement than LRU, and it stores a lot less state. Okay. So rather than n bits of information that store an access time, what I store is 1 bit of access information, right? And that bit is either set or cleared. When I want to locate a page to evict, what I do is I need to cycle through all of the physical pages that are available. And for each one of them, if the page access bit is clear, then I evict that page. If the bit is set, then I clear the bit. When do well, it says right up there on the slide, right? Just to back up, because I missed this. The bits are set when I load the entry into the TLB. So now the process of handling a TLB fault also involves setting this 1 bit on the page table entry, right? So it seems intuitively like this algorithm can get stuck in a loop. Can this algorithm get stuck in a loop? What happens if, when I go to start my clock, every page in memory has its access bit set? What will happen? What will the algorithm do? What's that? It'll clear them all, and then what it'll do? Well, it won't evict them all. It's only looking for 1 page, right? Yeah. Keep in mind. Sorry, I should have said this up here. If the page is clear, evict that page and stop. Right? Sorry. Yeah. Like, throw all you pages out of memory. I was looking for 1, but I found so many. Right? No. It's just looking for 1 page. So if it's clear, I evict the page and stop. Right? That's when the algorithm halts. So if all the pages are dirty the first time I go through, they all get cleared. And then I loop back to the top, and I end up taking the first page. If it's still clear at that point, it might have been set while I was looping, right, by some other process or another core. All right, so like I said, here's our clock, right? And let's say that these are the available page table entries because they're green, clearly. And that's where my clock pointer starts, right? So what does the first iteration of the algorithm look like? I'm looking for a page to evict. Which page am I going to pick? So I'm going to examine this guy. This guy's set. I clear it, right? I go here. This guy is clear, so what? That's my page, right? The next time the algorithm runs, right? Clear, clear, evict, right? Now, what I'm not showing here, and I should, is that as the algorithm, in between iterations of the algorithm, right? So after I selected this page and evicted it, time goes by, right? I may not need to evict another page, and these bits may be set again, right? So the property of the algorithm that prevents it from ever not being able to halt is that it's clearing bits as it goes, right? So if we look at if you can imagine the clock algorithm and you're watching your system, and you're watching the hand of the clock sort of spin around through all the physical pages, right? Keep in mind, too, the nice thing is that I don't have to walk all page table entries. I only have to walk physical pages, right? I probably need access to the page table entry for the physical pages. But I don't need to walk through all the physical pages because they're not all in memory, right? The pages I care about evicting are the ones that are in memory, not anything. So let's say that I was able to see this algorithm running and the clock hand was moving slowly. What would that mean? Slow moving clock hand. Yeah, James.
Yeah, can we loaded pages into memory that aren't being used very much?
Well, okay. I mean, okay. Let's say the system is actually quite busy, but the clock hand is still turning slowly. Yeah. Yeah, it just means that the system isn't experiencing a lot of memory pressure, right? The pages, I'm not having to evict very many pages, right? And when I do evict a page, right, the clock hand isn't having to turn very far to find one, right? What if I see the clock hand spinning around like madly? What does that mean? What could produce that kind of behavior? What's that? So it can, I mean, it's always going to find one, right? But yeah, so it's actually having to check a lot of pages before it finds one, right? And I mean, that could, in potential cases, indicate thrashing, right? So by the time I find one, by the time that page gets back and forth to disk or to disk, right? A bunch of other pages in memory have already been touched, right? And so I have to go a long way before I find another one, right? All right, any questions about page replacement? Pretty much done these algorithms. Adam?
I noticed in your diagram, the clock's hand maintained its position between
Yeah.
clearing pages. Is that part of the algorithm to start looking for pages at the same spot?
Yeah, you would probably implement it that way, right? Otherwise, you're biasing your eviction. Otherwise, your processes don't want pages with small physical page numbers, right? Because those always get thrown out first, right? But yeah, no, I actually think it's I think it's inherent to the algorithm to always starts and stops at the same place, right? Because eventually, I want to give every page the same chance to be evicted, right? That's a good question. Yeah, Mac.
Won't the clock only turn rapidly for one revolution because when you clear all those bits, so then they'll be.
So yeah, so if the clock end is continuously turning rapidly, what it means is I went through all the pages that had been accessed, right? I found, so imagine that it's turning almost a full revolution every time, right?
Yeah, I guess that's what I can imagine.
So what that could mean is that I found a page to evict, right? As I was evicting that page, every other page on the system was touched, right? So they were all accessed. I have to flip all the way around again, right? So at that point, the clock algorithm is almost, it's not quite random, but it's almost just picking pages sequentially, right? Because at that point, I mean, one way of thinking about this is that at that point, the clock, our effort to do LRU with one bit has failed, right? Because every page keeps getting touched in every interval, and so I have no way of knowing what a good page to evict is, right? Does that make sense? I mean, LRU only has this one bit of information that it could use to store access time. So if in each interval every page is touched, then it's I don't know, I'm just going to pick the first one that I happen to clear. Right? It's a good question. Any other questions? Yeah. You could use
Only one more bit.
interesting. The 2-bit clock. I have to think about how that would work. Yeah. Yeah. I mean, the nice thing about the clock, though, is it can stop as soon as it finds a bit, right? Because then you're back to having to do a min, and that's all. Yeah. That's interesting. Well, you could spin on the inner bit and then the outer bit. Yeah. I have no idea what that would do, but it sounds cool. Hey, good questions. All right, so I want to finish up VM with just one more little design exercise that we haven't talked about. It's been on exams before, so it won't be on an exam this year. And I thought it's a neat application of VM that ties together a couple of the things that we've talked about, right? So how many people remember the problem with fork? Remember our old problem with fork? I know this from a while ago, yeah. Yeah, so when a process calls fork, I have to copy the entire address space of the parent. So now let's say the parent has n pages allocated in its address space. How many pages do I need to find? N, right? And we just talked about all the work I might have to do to create free memory on the system. So in the worst case, that means I have to swap n pages out to disk, right? And that could cause a pretty big disruption in how the system works, right? And then what's even worse about this, right? So I did the work in fork, I found the memory, I've got the child in a new address space, and then what happens? Yeah, and then it calls exec right away. Well, it's like, I don't want that address space. You just went to all that trouble to get me, you know? Okay, so can we fix this problem? Yeah. Of course we can, right? But how is the question. The goal here is not to allocate any memory during fork. But remember, fork creates a new private copy of the parent's address space. So I need to make sure that the parent and child can make independent modifications to their memory that are not visible to each other, right? If I just did the dumb thing and I just said, hey, everybody, you guys can share pages, right? That would not work because then writes to local variables on the child would be visible to the parent, and that's not what I had in mind, right? But here's what we do, right? So I wish I had a diagram for this. I didn't have time to make one. But during fork, I take all the child's new page table entries and I point them to the same physical memory, right? This sounds like, you know, we're doing this bad thing that I just mentioned, which is that we're allowing the two processes to share memory that we shouldn't be allowing them to share. But we'll come back to this, right? As long as the child and parent are just reading, this is fine, right? Because they're not making alterations to the memory, and so the memory looks private, right? If I read from a page of memory, I have no way of knowing how many other people are sharing that with me. And I can't see any of their accesses to it as long as they're reads, right? Now, as soon as either the child or parent modifies the contents of the virtual page, I have a problem, right? Now I need two copies, right? Now essentially you can think of it as the versions of these pages have diverged, right? So now the parent needs to see one version of the page, the child needs to see another, right? And this is when these systems actually copy pages, right? This is why it's this technique, which we sort of hinted at before, is called copy on write, right? When the pages are modified, that's when I make my copy. Here's the question, though. How do I make sure that the operating system gains control in time to get this to work? I told you how to do this. I left out one minor little detail. Yeah? Yeah, so the trick here is that all the pages up here, regardless of what their permissions were when the fork happened, get marked as read-only in the TLB. Meaning that the TLB is now my friend. The TLB will tell me when those pages get written to, right? When the page gets written to, that's when I actually need to go out, find an extra copy for whoever's writing to it, make a copy of the original page, and update the page table entries. This actually is quite useful even for processes that don't call exec right after fork, right? Why would that be? Think about like a web server that forks off a bunch of different copies of itself to handle multiple connections. Some of them do something like this. They also use threads. Why is copy on write even useful for for a situation like that. I mean, it's clear why it's useful for exec, right? Because in exec, frequently the first thing the child will do is run the exec code, which is just a read operation. And then when I actually go and blow away the address space, all I have to do is remove all the copy on write, annotations I had made, right? But why is this useful even for processes that do fork and want to have multiple copies of themselves? Yeah.
Saves a lot of memory.
Why?
Because on the memory that read only has to be there. There are no duplicates for the read-only part.
Yeah, and what's the read-only part of my address space?
Of the code section.
The code, all like static variables. Yeah, so like, even if I do this and the child doesn't call exec and actually goes off and is trying to live its parent's life, this can still be a good trick because only the memory that the child needs to see as private is actually copied, right? The rest of it, including all the code and the shared libraries, static read-only variables, all that stuff, is all shared with the parent, right? All right, so now we are. Any questions about copy on write? Copy on write's a neat little trick. You are welcome to try to implement this for assignment 3. It is possible. I did it. Anyway, so next time we will start talking about disks.